sklearn, model selection, crossvalscore. Description. The crossvalscore function in scikit-learn provides a convenient way to evaluate the performance of a machine learning model through cross-validation. It splits your dataset into multiple folds, trains the model on a subset of the folds, and evaluates its performance on the remaining folds. This process is repeated for each fold, resulting in multiple performance scores that provide a more robust estimate of the model's generalization ability compared to a single train test split. Inputs. Estimator. This is the machine learning model you want to evaluate. It can be any model supported by scikit-learn, such as logistic regression, decision tree classifier, random forest regressor, etc. X. The input features of your dataset. Typically a NumPy array or pandas data frame. Y. The target variable you want to predict. Also usually a NumPy array or pandas series. CV. This parameter determines the cross-validation strategy. You can specify the number of folds, e.g. CV5 for 5-fold cross-validation. A specific cross-validation generator, e.g. K-fold, stratified K-fold, or a predefined list of train test indices. Scoring. The evaluation metric you want to use. This can be a string representing a standard metric, e.g. accuracy, F1 macro, R2, or a custom scoring function. Outputs. Scores. An array containing the performance scores for each fold. The length of the array will be equal to the number of folds specified in the CV parameter. Steps. Data splitting. The data is divided into the specified number of folds. Model training and evaluation for each fold. The model is trained on the data from all other folds and then evaluated on the held-out fold. Performance aggregation. The scores from each fold are collected to form the output scores array. Metrics. Accuracy. The percentage of correctly classified instances for classification problems. Precision. The proportion of correctly predicted positive instances out of all instances predicted as positive. Recall. The proportion of correctly predicted positive instances out of all actual positive instances. F1 score. The harmonic mean of precision and recall, providing a balanced measure of both metrics. Mean squared error, MSE. The average of the squared differences between the predicted and actual values for regression problems. R squared. A statistical measure that represents the proportion of variance in the dependent variable that is explained by the independent variables. Visualization plots. Box plot. To visualize the distribution of scores across different folds. Histogram. To understand the frequency distribution of the scores. Fine-tune parameters. CV. Experiment with different numbers of folds or alternative cross-validation strategies to find the best balance between computational time and robustness of the performance estimate. Scoring. Choose the metric that is most relevant to the specific problem you are trying to solve. Uncertainty methods. Confidence interval. Calculate a confidence interval around the mean score to quantify a uncertainty in the performance estimate. Bootstrapping. Resample the data multiple times and perform cross-validation on each resampled dataset to get a distribution of scores, allowing for the estimation of the variability in the performance. Challenges and fixes. Challenge 1. Overfitting to the training data. Sample use case that resulted in challenge 1. A model that achieves high accuracy on the training data but performs poorly on unseen data. Fixes to challenge 1. Use regularization techniques like L1 or L2 penalties to prevent overfitting. Increase the size of the training dataset. Experiment with different model architectures or hyperparameters. Challenge 2. Data imbalance. If the classes are imbalanced, the model may be biased towards the majority class. Sample use case that resulted in challenge 2, a model that predicts the majority class for all instances in a dataset with highly imbalanced classes. Fixes to challenge 2 use techniques like oversampling the minority class, undersampling the majority class, or using a cost-sensitive learning approach to address the imbalance. Challenge 3, limited data. If the dataset is too small, the performance estimates from cross-validation may be unreliable. Sample use case that resulted in challenge 3, a model that shows high variance in performance estimates due to limited data. Fixes to challenge 3, consider using data augmentation techniques to increase the size of the dataset. If possible, collect more data. Challenge 4, computationally expensive. Cross-validation can be computationally expensive, especially for large datasets or complex models. Sample use case that resulted in challenge 4, a model that takes a long time to train and evaluate. Using cross-validation. Fixes to challenge 4, consider using a smaller number of folds, reducing the number of features, or using a less computationally expensive model.